So either everyone has it right or everyone has it wrong.
It should be right.
It's logic. All right, it says that PQ is 24. Well, since OM starts at the center and is 90 degree to this chord, it means it bisects it. 90 degree and starting from the center means it bisects it. So we have 12 and 12. Well, that means that we have a right triangle with 12 and a hypotenuse of 13. You either know that there's a Pythagorean triple, which would be 5, 12, 13, or you can do the a squared plus b squared equals c squared. You should end up with OM being 5. Should be some happy people. All right, our next one says find the measure of CD. Well, to get the measure of CD, we're going to break some stuff down. First of all, see this 90 degree symbol here? It's 90 degrees. It's a 90 degree central angle, which means the arc it subtends is also 90 degrees. So from B to D, you have 90 degrees. Now to go a little further, since these two chords are the exact same length, it means the arcs they subtend will also be the same. So BC must be equal to CD. So that means BC is 45, and CD is also 45 degrees, so we should have 45 degrees for CD. What happened?
Oh, wait.
Did you put 90 as the answer? Yep. We're looking for CD, not BD. If you're ever not certain, you come up with all the other measures as well. If you're not sure if this is 90 degrees, because I heard some people like, yes, it was 90 degrees. You could check that because D to A is 180 degrees. Well, this must be 90, this must be 90, so this arc has to be 90, and that arc has to be 90 as well. So you can actually check your work sometimes with that 180 and knowing you're splitting in half. All right, questions on that? All right, then let's go over questions from homework. We got plenty of time to do it. Today's lesson is pretty quick. Doesn't mean it's easy. Just means it is quick. Life.
28.
I don't know how to do that one. Other questions? No, I'm just kidding. We're going to ask for 28 again?
Yeah, me too.
You're just going to keep saying 28. All right. X, Y, and Z. X, Y, and Z are points on circle P. Let's draw a circle P to start off with. Circle P. All right, then let's go back. X, Y, and Z are points on circle P such that triangle XYZ is equilateral. So we have an equilateral triangle somewhere in here. So let's go ahead and draw that action. So let's draw 3 points that kind of look like an equilateral triangle. That looks like good. And we're going to call it X, Y, and Z. Let's connect these. Well, that doesn't look, I guess it's close to being equilateral. But it's equilateral. All those sides are the same length. All right, if the radius of circle P is 6, what is the perimeter of triangle XYZ? All right, this is where you got to really think about what radius means. So that means the distance from here to the edge of the circle is going to be 6. However, if I draw my line right here, that doesn't help me because it doesn't connect to anything important. So it's always a good idea to try to connect your radius to one of the points. So let's just connect it to X. We could have connected it to Z and we would get the same answer. We could connect it to Y and we get the same answer. We connect it to X. We'd all get the same value. So let's just start with X. Let's just start with X and say that, okay, our radius is 6, so this distance is 6. All right, but that doesn't help me too much because I don't have any triangles or anything like that. So let's extend a radius to Z, which is also 6. All right, now I have a triangle, but it's not a right triangle. So what I'm going to do is I'm going to drop a perpendicular. Now I have a 90-degree triangle. Do we all see this 90-degree triangle here? Well, here's the problem. I just know the hypotenuse. I just know the hypotenuse. The other way you can know one side is if it's a 45, 45, 90, or a 60, 30, 90. Let's think back at what an equilateral triangle is. What's the measure of every single angle of an equilateral triangle? Yes? It is 60 degrees. So this angle right here is 60 degrees. It doesn't look it, but your point that's in the center of the circle is going to bisect this angle. It's going to bisect this angle, and it only makes sense because if I draw one more up here, every one of these angles needs to be the same. So it's going to split it up into a 30 and a 30 degrees. So this is 30 degrees. This would also be 30 degrees, which makes this 30 degrees, which would make this other side 30 degrees, but I don't really care about that. What I care about is this triangle here. I'll pull out that triangle. Okay, so we have a right triangle. That's a 30, 60, 90 degree, and it has a hypotenuse of 6. Well, that's everything we need to solve. Remember, the one across from the 90 degrees is, what is that one?
No, 2S.
2s, yes. So the one across from 90 degrees is our 2s. The one across from 30 degrees is going to be s. Like, what's the one across from 60 degrees? S radical 3. Well, if 2s equals 6, then s equals 3. Which means s square root of 3 is going to equal 3 radical 3. So that means this length right here is 3 radical 3. Remember, that's just half your length, though. So this distance right here is 3 radical 3. This distance here is 3 radical 3, 3 radical 3, 3 radical 3, 3 radical 3, 3 radical 3. So we have 1, 2, 3, 4, 5, 6 lengths that are all 3 radical 3. So you just do 6 times 3 radical 3, and you're going to come up with 18 square root of 3s. Like, does that make more sense? Yeah. Tyler, does that make more sense since you were going to ask that? It's all about kind of coming up with those right triangles. And, hey, worst case scenario on the test, you come up with the right triangle and you're not sure how to solve it. At least you have a drawing, and you get points for knowing that you can draw a right triangle. You just weren't sure it was 30, 60, 90. All right, more questions. Sahaj. 27. All right, 27 says we're going to start with circle T. It's not like Mr. T, but more of a circle. Circle T. Boom. It's not Sean T. That's too much working out. All right, so we have a circle T with a diameter BC. Let's go ahead and draw our diameter BC, because I know exactly what has to happen with the diameter. Diameter has to go through the center. So I can at least get that part right. If I get everything else wrong, I know my diameter BC is correct. All right, what do we have to do with this diameter? So it says the diameter BC is perpendicular to chord MN. Now, they didn't say that MN is also a diameter, so I'm going to assume it's not a diameter. It might turn out to be, and when we solve it, we'd actually figure it out. But we're going to assume it's not. So let's draw MN being perpendicular to it. So let's just draw it over here, or on the other side would work as well. So this will be my MN, and it's 90 degrees. All right, what else? They said it intersects at point E, so let's call this point E. If TE is 8 squared of 3, that's not fun, and BN is 150 degrees, then what is BC? All right, so BN is 150 degrees. And this little length TE is going to be 8 square root of 3. And they want us to figure out what the length of BC is. So that entire line, I need to figure out what that entire line is. Okay. The cool thing about finding out this entire line is this is a diameter, correct? A diameter is made up of two radii. So that means I really just need to figure out the distance from T to C and multiply it by 2. So at least it makes our job a little easier. So in reality, I'm just trying to find EC. That is all I need to find is EC. All right, let's push through. Let's go ahead and create a right triangle because it's always a good idea. It's always a good idea to connect our center to one of our points. I'm going to connect it to that one, and you'll see why in just a second. That creates my right triangle that I'm looking for, correct? And I picked that specifically one because this is an angle that goes to the center of the triangle, which makes it a central angle. A central angle is going to have the same measure as the arc it subtends. Well, that arc distance is 150 degrees. So that makes this angle BTN 150 degrees as well. Well, if that's 150 degrees, then this is, oh no, it's a 30 degree, which makes it a 30, 60, 90 degree triangle. And now the one across from our 60 degrees is our S squared of 3, which makes our S 8, correct? And the one across from 30 is just going to be our 8. But that's not really what I care about. I care about the one across from the 90, right? So we come up with our EN is going to be 8, because that is the one across from our 30. The one across from our 90 is 2S, so that's going to be 16. That's a radius, correct? What's 2 times a radius? Our diameter? What was that?
32.
It'll be 32. Do you get how I jumped to that?
Yeah.
All right. So we have 16 as our radius. Well, BC is a diameter. Which equals 2 times our radius, which is going to equal 32. All right, if you didn't connect all those pieces on the test, like let's say you just drew this triangle and you kind of came up with some of the stuff, you get a lot of the points. All right, sometimes you just have to remember what we're solving for. Radius, diameters are going to be really big. Other questions from the homework? Will, was that one yours? Does that make sense?
Yeah.
Okay. Questions going once? Going twice? All right, sold to the highest bidder. All right, today we're going to talk about tangent theorems. Remember, a tangent line is one that just intersects a circle in one place. If it intersects in more than one place, it's a chord. All right, so tangent intersects at one place. So our first theorem is a line is perpendicular to the radius of a circle if and only if the line is a tangent line. So that means any tangent line is perpendicular to the radius. So let's draw that picture. So let's draw circle C. And let's draw a line tangent to it. Tangent means it can hit one place. We'll say it hits at point T, because that will match what I have on the left-hand side, and this is R. All right, this says that CT is perpendicular to TR. So CT would be that radius, which will be perpendicular if, see these double arrows? That stands for if and only if. It means it goes both directions. That is our if and only if. TR is tangent to circle C. So you can say the statement in any direction you want. You could say CT is perpendicular to TR if TR is tangent. And you can also say TR is tangent if it's perpendicular to the radius. So the big takeaway here is any tangent line is going to be perpendicular to a radius or a diameter. Anything that goes through the circle. So once again, any tangent line is going to be perpendicular to a line that goes through the center, like the radius or a diameter. That's important. It's important to recognize, once again, a tangent line is perpendicular to a line that goes through the center. I say it a lot like I did yesterday, because the more you believe it and you can see it in the picture and you think of it in your head, the easier these problems become. Once again, if you see a tangent line and you see a line going through the center, you should immediately go, okay, it's 90 degrees. Whether it's part of the problem or not, you should immediately think that. So you see a tangent line, think 90 degrees to that center line. All right, the next one says, two segments drawn from the same circle that intersect outside the circle are congruent if and only if they are both tangent to a circle. Let's go ahead and draw that picture and what we're talking about. So we're going to draw a picture D. And then we're going to draw two tangent lines that intersect outside of the circle. The easiest way to do that is actually to come up with a point outside the circle. I'm going to call it G. Now draw two lines from G that are tangent to that circle, so that means they both hit at one location. And it kind of looks like you're drawing a hat if you draw it on top. It's like a sideways hat. If you turn your head sideways, it's a hat. Right? Right? No? No one sees that? All right. Just weird, I guess. I'm going to call this A. I'm going to call this B. If you have two tangent lines that intersect outside of your circle, that means the lengths of those segments are going to be congruent. So that means BG is going to be congruent to AG automatically. As soon as you have two tangent lines that meet outside, you're going to know that both those segments are congruent. I'm going to put on here, because I told you to think about this. Remember that both these lines are actually 90 degrees to your radius as well, because you should think that too. When you see a tangent line, you should think 90 degrees to the center line. And now you could think of, if you have that little hat shape, hey, both of those segments are congruent to each other. Two very important theorems. They're a little easier than the ones yesterday, but they're just as important. All right, let's go ahead and use them in two problems. Do anyone have questions on either one of those two drawings, or what's going on? All right. So our first one says that we're supposed to solve for A. We need to solve for A. A slightly harder problem than it looks. So the first thing I'm going to look at is, hey, we have two tangent lines, correct? So we have two very important things we just learned. The first thing is, both of these are going to be the same length. Might not be necessary, but it's important. The other thing I'm going to note is this is 90 degrees, and this one is 90 degrees. Well, when I see 90 degrees, I'm thinking different shapes that we have, and the most important shape we have with 90 degrees is a triangle. A right triangle is usually the one that I just need to know a certain side, a certain measure or something like that, and we can get the rest. Well, what I'm looking at right there is actually two right triangles put together. Two right triangles put together. In other words, if I just go dun 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 dun, we have two right triangles. And rather than this being 36, I'm cutting it right in half. So it's actually 18 and 18. So that would give me 18 degrees and 18 degrees. Okay, that's 18 degrees. That's 18 degrees. I can do all of this because these are similar triangles. So we have 90, we have 18, That gives me 108. What's the measure of this right here?
72.
72. What's the measure of this one?
72.
72. Yeah. So they're both 72 degrees. So that means our A is going to be 72 plus 72, which is going to equal 144 degrees. Surprisingly enough, we did have to use both backs. It didn't look like it, but we did. We had to have that this was the same length. Note, we also used, I kind of buried it without really going over it. We also used that the radius was the same, and we actually used side, angle, side to say both of those triangles would have to be the same. That's how I knew we're dividing 36 in half. I used side, angle, side to say, hey, both those triangles have to be congruent. All right, our next one. Well, there's no line that goes to the center, so nothing's 90 degrees. Or nothing that I know of. But what I do know is that, hey, if two tangent lines intersect outside a circle, that means that both of them are congruent in length. Well, if they're congruent in length, it means that that's an isosceles triangle. The base angles of an isosceles triangle are congruent. So that 48 degrees and the one with nothing on it must also be 48 degrees. And that's because of our isosceles triangle theorem that says isosceles triangles have base angles that are congruent. Well, now I just have a big triangle with a 48, 48, and a missing B. Well, that's going to make B equal to 48, 48, that'd be 84. Questions? All right, then the rest of the time is for you to work hard, ask questions. They aren't always as easy as these two. In fact, that first one was a little difficult until you saw you could divide it into two right triangles. There are some tricky ones.